We're also going to look at tangent segments. So now we're going to open this second applet. And again, you could type that in, or hopefully you have the link pulled up from our agenda. So in this case, you can see that we have two tangent lines, right? So line EC and line DC are both tangent lines. Can you tell why they're both tangent lines or how we know that? Remember from our last tutorial that a tangent is always going to be perpendicular to a radius of a circle. And in both of these cases, I can see that line DC is 90 degrees with our radius AD, and line EC is perpendicular or 90 degrees with our radius AE. So the question here was, how do we know line CE and line CD are tangent lines? We can say they are perpendicular to a radius of the circle. We want to move point C and observe the measurements. Keep C outside the circle so things don't disappear. So as I move point C, I can see, first of all, that my measurements for these angles remain 90 degrees. So I'm keeping the lines tangent. But I can also see measures for the distance from C to E and the distance from C to D. So C is this external point connecting to the point of tangency here, E, and connecting to the point of tangency here, point D. And I can see that both of these happen to be the same measurement. So if I focus on only the segment CE and the segment CD, I can see that segment CE and segment CD are congruent. They have the same measures. So what is true about two tangent segments from the same external point? So the fact that both of these had the same external point and they were both tangents, we can say that those two segments, so not the whole line, but the measure of the segment, is going to be congruent. So we can say that in this case, for instance, CE is congruent to CD. So they are congruent to each other. And again, this is going to be true about any two tangent segments that stem from the same external point to a circle. They're going to be congruent to each other. So we can use that to find missing information. So we have a circle here. And we have this tangent, again, just like earlier in this lesson, anything that appears to be tangent, we are going to say is tangent. So this would be a 90-degree angle, and this would be a 90-degree angle. So since both of these tangents stem from the same external point, that means that this segment here is congruent to this segment here from the external point to the point of tangency. So this segment is congruent to this segment, or if it's helpful to highlight that, that's this segment is congruent to this segment, which tells me then that 6x plus 7 should equal 8x minus 7. So 6x plus 7 equals 8x minus 7. Notice we didn't need anything with the radius. It doesn't need to be applied into our problem. So to isolate x, we could take away 6x from both sides, which means we would have 2x minus 7 equals 7. Add 7 to both sides, so 14 equals 2x. And dividing by 2 tells us that x equals 7. Over here, I know this looks pretty intense, but hopefully you can see that we have a circle here. And we actually have 4 different lines that are all tangent, or segments that are all tangent to the circle. So we call this a circumscribed polygon, in this case, a circumscribed quadrilateral. And that just means that each of the sides of that polygon are tangent to the circle. So we want to find the perimeter of the circumscribed polygon. But what can be beneficial is to figure out all the different pieces that are congruent to each other. So because this tangent segment here goes to this external point, and so does this one, that means that this segment, only from that point of tangency out and from this point of tangency out, those two are congruent. In the same way, I can say that because these two share the same point of tangency, or I'm sorry, the same external point, then their segments to the point of tangent C are also congruent. So this one is congruent to this one. And then we can see that this would be congruent to this. So 1, 2, 3, and 1, 2, 3. And finally, we would have that this segment here is congruent to this segment because, again, those two are tangents that share the same external point. So if we go through, and I actually might clear out some of these colors just so that you can see a little bit more of what's going on just at one time. So we can do more with that if you need me to draw those again. But because this is 11, it tells me here this entire segment is 14.7. So just the orange part here is going to be 11 units. So if I take 14.7 and I subtract 11, I can figure out then what this piece is that we will make. Let's do yellow here. And therefore what this piece is, since those two are congruent. So 14.7 minus 11 is 3.7. So this little yellow segment here is 3.7, and therefore so is this one, because those are congruent since those are two tangents that share the same external point. Because this distance all the way from this point to this point is 13.1, I can take 13.1 and subtract 3.7 to get this part here. And therefore that's the same as this point there, or that segment there. So when I subtract 13.1 minus 3.7, this part here is going to be 9.4, and therefore so is this segment. Since this segment over here is 7.1, that means that this one is also 7.1. So we can see all the different perimeters, or all the different lengths, I'm sorry. So in order to find the perimeter, we want to add all of those together. So the two orange segments are both 11. So we have two segments that are 11 units long. Plus our two yellow segments are both 3.7 units. So plus 2 of the 3.7s. Plus, in this case, this is 9.4 and so is this. So 2 of the 9.4s. Plus 2 of the 7.1s. So if I add all of those together, our perimeter should be 62.4 units.